All right, maybe we can go and get started. So the plan for today is to continue our discussion of computer vision. So just to remind you, in the previous lecture, we discussed optical flow, which is the apparent motion of objects as they appear in some kind of sequence of images that a camera is capturing. And we talked a little bit about the kind of biological inspiration for thinking about optical flow. And in this assignment, you're thinking about how you can use optical flow to compute velocity of the drone and also time to collision to do obstacle avoidance, for example. So we spent the lecture, I guess last lecture, using kind of like old school methods, the Lucas-Kanade algorithm in particular, which was developed around like 30 years or so ago. And we saw some of the challenges, right, of doing things in a kind of almost like model-based approach where we think about the physics of the problem or make some assumptions and then come up with the algorithm to compute the quantities that we want to compute. And the main challenge, I think, has to do with the fact that we made some relatively strong assumptions when we implemented the Lucas-Kanade algorithm for optical flow. In particular, this like spatial coherence assumption, so optical flow of one pixel is similar or the same of the optical flow of pixels around it. And then we also assume that things were moving relatively slowly in the scene. And the last assumption was on this color constancy. So objects, when they move, like basically appear the same after they've moved. So none of these assumptions are like truly satisfied, right, in the real world. And if the assumptions break, then the approach can work pretty poorly. And I guess that's something you should try to do as part of this assignment. Maybe get a video where some of these assumptions are not completely valid and see exactly how the approach breaks. So what we're going to start doing today is talk about learning-based approaches to computer vision, specifically deep learning-based approaches to computer vision. And maybe before we start, I guess I'm curious, just to get a quick poll. So I think year to year, the number of people who've seen some deep learning, I think, keeps increasing. So I'm just curious kind of what the fraction is this year. So how many of you have already seen, let's say, like convolutional neural networks? And okay, all right, not everyone, some fraction. All right, so yeah, I think this is a bit of a challenge because some of you probably like haven't seen much deep learning. Some of you've maybe taking courses in computer vision or in machine learning where you've seen some of this material. I'll try to make things a bit more kind of robotics focused, but if you have seen some deep learning before, then there might be some overlap for sure. All right, so I guess just a quick kind of intro to the recent history of deep learning. So as maybe some of you know, there was a kind of like big shift around 10 years ago, so 2012. Particularly in the context of image recognition. So these are error rates for doing image classification for the ImageNet data set. So ImageNet is a large, well, I guess at least at the time it was kind of a gigantic data set. By today's standards, maybe it's not as gigantic, but it's a relatively large data set of images corresponding to different objects and classification or classes, labels corresponding to those objects. So back in 2010, 2011, the error rates were relatively high, so 25 or somewhere between 20 and 30%. And then suddenly in 2012, people started using deep learning-based techniques to really get like state-of-the-art performance on image recognition. And you can see that the error rates kind of pretty dramatically go down from 2011 to 2012, so it jumps from around 23% error, which is pretty high, to 16 or so percent, which is significantly lower. And the error rates have kind of continued to go down. So in 2017, which is already like 5 years ago, the error rates were down to about like 2% or so. And human level performance on this image recognition task, if you get a bunch of humans to spend like weeks like understanding the different kinds of dogs and different kinds of cats and all the different kinds of objects that appear in this data set. So human level performance was about like 5%. So we surpassed human level performance back in 2015 or so more than 7 years ago for this data set at least. Okay, so I guess what's led to this revolution in machine learning? So I think there's three things roughly, or three categories of things. The first thing is data, lots and lots of data. So I already mentioned this ImageNet data set, which had a massive impact on the field. There's a whole bunch of other data sets for pretty much any computer vision or machine learning task that you can imagine. So I guess these are some examples from ImageNet. So you can see that it's relatively like obscure categories of objects, and they're kind of hierarchically categorized. So going from like mammal to placental, carnivore, canine, dog, and specific kinds of dogs, and specific kinds of vehicles, specific kinds of cats, and so on. More relevant, I guess, to robotics is this cityscapes data set. So these are images from different cities, and associated with each pixel is a semantic label. So with each pixel, there's a label that says road, or pedestrian, or bicycle, or tree, and so on. And so these are kind of like densely labeled images, densely labeled with the corresponding semantic categories. So like I said, different cities, 50 different cities, and pixel level annotation of different semantic categories. So we talked about optical flow in the last lecture, and I think someone asked other data sets for optical flow. So there's one called Flying Things 3D. So these are like synthetically generated images or videos of a bunch of kind of random flying objects in simulation. So I guess you can see in some of the images there's like a car, there's a whole bunch of random things like sofas and other things that are like flying around in 3D, synthetically in simulation. And then you're basically generating what an image would look like, or what a video would look like if you had some camera looking at these randomly moving 3D objects. The nice kind of thing about this is because everything is happening in simulation, you can calculate the ground truth optical flow. Like you know exactly where like each point in the scene is moving, and so that's your kind of label, which you can then use machine learning techniques to go from a sequence of images to like these labels corresponding to optical flow. I guess optical flow is like harder to do with real world images. You can do it if you had a motion capture system, for example. You could place like markers on some object, move that object around, track the object using a motion capture system, so you know exactly like the ground truth like motion of the object. Put a camera kind of on the side and see like what different motions correspond to in terms of video. So that's one way to do it, but that's like pretty data intensive. Like here you can generate lots and lots of videos of kind of random objects doing random things, and this seems to work reasonably well for optical flow. I guess more recently some autonomous car companies have also started making some of their data openly available. So there's the Waymo open data set that I think was released maybe a year and a half or so ago. So this has a whole bunch of things. So it's not just for computer vision, but it's also for pedestrian trajectory prediction. So they have like real world data of pedestrians and bicycles and like other cars kind of moving around next to an ego vehicle that's collecting all the data. And so this is like important if you're trying to do autonomous navigation in cities. So if you want to use some like planning algorithm, one kind of useful thing that you might want or you probably do want your autonomous vehicle to do is predict what other agents in the scene are going to do. Like, is the pedestrian going to stop? Is the pedestrian going to move, and so on? So these kinds of data sets allow you to learn to make those kinds of predictions. And so this is just like a quick kind of snapshot of different data sets that are available. As I mentioned, there's tons and tons of data sets for all kinds of different tasks that you could possibly imagine. And more specifically, it's not just massive amounts of kind of generic data, but a lot of the success behind deep learning and in computer vision in particular and other areas as well comes from the fact that we have labeled data. So with image recognition, the image in a data set and other data sets have corresponding to each image some label, like the category of object that's represented in that image. With the optical flow, as I mentioned, there's kind of like ground truth optical flow that you can get if you're doing things in simulation. With the semantic data set as well, kind of people have, like humans have annotated the pixels with the different semantic categories like pedestrian, road, and so on. So nowadays there's a whole kind of economy, a whole ecosystem around data labeling. So there are companies that basically do this kind of as their main service. You can get some raw data without labels. You can kind of describe what you want as labels, and yeah, there's companies of people doing this kind of annotation, partially by hand, but also partially automated. So with the semantic labeling example, one thing you might do is segment the image, so you can break it up into different portions, and then the human just needs to say what the label is for just the segments, instead of going like pixel by pixel and labeling like each pixel and saying exactly what it is. So yeah, I guess there's tricks to make this faster, but it's still pretty like human intensive to generate high quality data sets to do this kind of machine learning. So yeah, I guess what does label data allow you to do? So it allows you to use supervised learning. So it allows you to learn in a supervised manner. So just to make this concrete, again in the context of image recognition, let's say you have some training data set, so a bunch of different images and their corresponding labels. What you can do is learn that mapping, right? So you can learn the function that takes as input some image and then outputs a category of object. And then at test time, so when you actually deploy this learned system, you can give it a new image that was not part of your training data set, and then you can ask what's the corresponding label, and you basically apply your learned function to get some prediction about what the label is. All right, so that's kind of one major factor that's made modern machine learning really successful. The other one is computation, so lots of computation, and more specifically GPUs, so graphical processing units, have really been the kind of computational workhorse for machine learning. Originally, these were developed for video games to make like graphics run faster for video games, and it turned out that a lot of the computations that you needed for that, like for video game applications, were also useful for machine learning applications. So they're particularly good at computations that are highly parallelizable. So if you're multiplying like big matrices with big vectors, a lot of the computations there are parallelizable. They're like relatively simple computations that you can like parallelize. So GPUs are particularly good at that. Yeah, so I guess this is just my desktop computer. It has like 4 GPUs. Which is something. I mean, you can do something with it, but if you're trying to do some like really large-scale things, nowadays people have servers with like hundreds of GPUs. Like particularly if you want to do anything in the context of large language models, or even for computer vision and other machine learning applications. Okay, so I guess that's the second major factor. The third major factor is neural networks, like algorithms and architectures. For neural networks. So I guess just a very quick kind of intro to neural networks, or the history of neural networks. Originally they were inspired by biological neurons. This is a very, very, very loose inspiration, and yeah, I would suggest not taking it super seriously. It's just kind of historically people were thinking about biological neurons, had some like very rough model of what a biological neuron does. It basically takes in a bunch of inputs, like from dendrites, and it has some outputs, and those outputs are then the inputs for other neurons and so on. But the actual neurons in our brain are significantly more complicated than what we call neurons in artificial neural networks. So yeah, I guess just as an example, this is the MNIST data set. So it's a data set of labeled images corresponding to digits, like handwritten digits. So each image is just a black and white or grayscale image, and there's a handwritten digit, and we have a label corresponding to each image. So yeah, I guess what happens, like the computation that happens is you take as input the image, like one of these handwritten digits, you pass it through a neural network, and that gives you some prediction, like some output for what we think the label is. So early neural networks, so back in the 1950s, that was kind of the first wave of neural networks, and specifically the perceptron machine that was designed by the person in the picture, Frank Rosenblatt. So this machine was actually connected to a camera that gave you a 20 by 20 image. So this is like super, super, super low resolution, right? I guess if your phone had a 20 by 20 camera, that you'd be very disappointed, but that's what they had to work with at the time. And he was trying to do, or his team was trying to do recognition of alphabets, so I guess similar to the MNIST data set. And this is the actual machine, like this is the actual like neural network. So it's a whole bunch of like wires that are instantiating the computation that this like perceptron machine is doing. Nowadays, of course, we don't have this. Like we just run a neural network on a computer. But at the time, they had to like physically build some machine with a whole bunch of wires that instantiated this kind of input to output relationship. So it takes in as input some representation of a 20 by 20 image. Those like electrical signals like pass through this like physical machine, and that gives you some output label. Okay, so all right, so I guess a single artificial neural network has this kind of general structure. So you take in a bunch of inputs. So the inputs here are represented by x. So you can think of x as just some vector in a finite dimensional vector space. You take each of the dimensions of x and multiply them by some weight. So you're essentially taking a dot product of a weight vector w with the input vector x, and then you add in some constant term, which is called the bias, and then you pass that through some nonlinear function f. So that's basically the main kind of computation that each neuron in a neural network does. So you just take the input x, you take the dot product of x with some weight vector w, you add in a constant, the bias term, so that gives you a scalar, and then you pass that scalar through a nonlinear function f. And we'll say kind of more about the specific choices of f in a little bit. So yeah, I guess just to make this concrete, let's think about a particular example. So let's say we're trying to do pedestrian detection, which could be useful, of course, for autonomous vehicles or other robotic systems. So let's say you have some data set, like someone has curated a data set of different images, each of which is labeled with a 0 or a 1. So it's a 1 if there is a pedestrian in the image, and a 0 if there's no pedestrian in the image. Okay, so let's say we have images of a particular resolution. So here we're going to look at RGB images. So each pixel corresponds to a three-dimensional vector, like the R, G, and B values. And just for the sake of concreteness, let's say we have like relatively low resolution images, so like 32 by 32 images. So each image, if you think of this as an input, corresponds to a vector that lives in Rn, where n is 3072. So each image is a point in this high-dimensional vector space, 3072 dimensional vector space. So what we're going to do, so I guess what I'm going to describe is just the computation that a single layer of a neural network does, and then we'll see how we can make this computation more rich. But just to focus on single layer neural networks, this is the computation that I showed you before. So we're taking each component of x and multiplying that by some weight wi, and then summing over all the pixels. Well, I guess not just all the pixels, but also like the three channels in the pixel. So we're summing from 1 to 3072. That gives us a scalar when we take this dot product between the weight vector w and the input vector x. We add in a scalar b, and then we pass that through a nonlinear function that I'm calling sigma here. So I guess any questions on this computation? So we're mapping an input which has dimension 3072 to just a scalar value. Questions on the computation? Go ahead.
The bias is applied after the addition, right?
Yes, yeah. So the bias is like outside the summation. Good. All right. Other questions? Okay. And yeah, I guess this is a piece of terminology. So that nonlinear function sigma is sometimes called the activation or just the nonlinearity. We'll discuss some specific choices for that in a bit. So if we define our weight vector w, so we can think of this as a column vector. So column vector that has dimension 3072. The input, if we think of that again as a column vector of dimension 3072, the bias is just a scalar. We can rewrite this computation as a dot product. So we're taking the dot product of the weight vector with the input vector. That gives us a scalar. We add in this bias term, that's another scalar, and then we pass that through the activation function. Okay, and the activation function is just a mapping from scalar to scalar. So here are some particular choices. What was our question? Go ahead.
Do the weights have to sum to 1?
The weights don't necessarily have to sum to 1. So there's some normalization that can happen using the activation function. So I guess here's one possibility for the activation function. This is just the sign function, sign. So if the dot product plus the bias term, so the input to sigma is positive, then sigma maps that to positive 1. If the input to sigma is negative, then you map that to negative 1. So this is one possibility for an activation function. I guess here are a couple of other possibilities. So you can choose a sigmoid function that's kind of a smooth version of the sign function. Which specific version you choose kind of depends on whether your labels are 0 or 1 or -1 or 1. In the pedestrian detection example that I gave before, that we'll I guess continue to use as a running example, I was saying that the labels are 0 or 1. So 1 if there is a pedestrian, 0 if there's no pedestrian. So then you might want to choose something similar to the left. If your labels are -1 or 1, then you might want to choose something similar to the right. Another, I guess, really popular activation function or nonlinearity function is ReLU. So this is the rectified linear unit. If the input to sigma is positive, then the output is just whatever the input is. So if your input x, let's say, or not x, maybe we can call it something else, like z is positive, then you return z. If z is negative, then you just return 0. So this is another kind of popular one. Yeah, there's a whole bunch of different options for nonlinearities. They make some difference, and it's important to understand what the different choices are. But yeah, typically it ends up not mattering that much. Like these nonlinearities that I mentioned tend to work pretty well. Question?
Is the value for sigma having symbolic meaning? Does it tell us the confidence?
Yeah, good. So especially for if you use a sigmoid nonlinearity, you can interpret the output as a confidence. So the output is some number between 0 and 1. So if the output is very close to 1, you can think of that as a confidence or you can think of that as expressing confidence that the label is 1, and if the output is close to 0, you can think of that as expressing confidence that the label is 0. You have to be super careful though about like interpreting what that means, because actually it means nothing, or it can mean something, but usually it doesn't necessarily have the kind of probabilistic like interpretation that you would want. So what you would want is some kind of like interpretation where if you have, let's say, like 95% confidence, like if your sigma value, like output, is larger than 95, you would want that for 95% of images, you get the correct label if you use that as kind of your threshold. But that tends not to be the case in practice. So you can like very, very loosely interpret it as confidences, but it doesn't, at least without further work, like it doesn't have the kinds of probabilistic interpretations that you would want. Yeah. Okay. Questions on other questions on that? All right. So I described the computation that one layer of a neural network does. There are a couple of kind of intuitive interpretations for what's going on with that computation. So one interpretation is that we're basically doing template matching. So if you think about the weights W as an image in its own right, so W, if you remember, has dimension 3072. So you can kind of rearrange that into an image that has dimension 32 by 32 and kind of RGB values. You can think of that, yeah, like I said, you can think of that as an input image. What we're doing when we do this like dot product calculation is just seeing how similar the input X is to the weight image W. And so if you basically learn these weights W for like an image classification problem using some like data set like ImageNet, or in this case CIFAR, these are the like weights if you kind of visualize them as images that you end up getting. So if you squint hard enough, they kind of look like the label, right? So I don't know which one is the clearest. They're not like super clear. Maybe the car one seems sort of like a car. So that's like you can think of that as the kind of like a canonical like template of a car. So that's the vector W. So if you're given a new image, X, we take the dot product of X with like this template image. And like the dot product is a measure of similarity. So the dot product is high. That means that there probably is a car in the image. If the dot product is low, then that means that there's probably not a car in the image, at least according to this template. All right, so it's a kind of like pattern matching, right? Like template matching. We have some template described by the vector W. We see how close the input image is to this template, and then we have a threshold that says yes, there is a car, or no, there isn't a car, based on that similarity metric. I guess, does that interpretation make sense? Any questions on that? Go ahead.
What's the point of the bias?
So in this case, there's no point really to. I mean, you don't need the bias term. It depends on like whether. Yeah, I guess it depends on like exactly what the nonlinearity like function is. So it becomes useful actually when you look at like multi-layer neural networks, which we'll do in a bit. But yeah, you can ignore the bias term, like just set it to 0 for this example. I guess maybe another answer comes from this interpretation. So another way to think about what a single layer neural network is doing is that it's doing linear classification. So we have like this function like W transpose X plus B. You can think of that as defining some hyperplane. So anything that's on one side of the hyperplane has W transpose X plus B being positive. Anything that has that's on the other side of the hyperplane has W transpose X plus B being negative. So we're basically dividing up the space of all images into two portions with a hyperplane. And the hyperplane is defined by the weight vector W and the bias term B. I guess if you think about it this way, then the bias term basically allows you to not have the hyperplane passing through the origin, which I guess could be useful depending on like where like the data lie in your space of images. So this is I guess a visualization of what I said. So like the red hyperplane, in this case we're just drawing a line, corresponds to like a car classifier. So anything that's on one side of the hyperplane, one side of the line, is a car. Anything that's not, anything that's on the other side is not a car. And then different lines, like different hyperplanes, correspond to different classifiers for different objects. I guess any questions on this interpretation? Okay. All right. So so we described just single layer neural networks, which are pretty limited. So I guess what can a single layer neural network not do? There's lots and lots of things that it cannot do. These are some examples. So if you think about two classes, let's say like pedestrian or not, or whatever the two classes happen to represent, that are kind of divided up in any of these ways, then you can maybe convince yourself that there's no single layer neural network that will classify each of these perfectly. So there's no line that separates the red from the blue, right? So if you look at the first image, any line that you pick, on one side there's going to be some red and some blue, and on the other side there's going to be some red and some blue. So there's no way to have a line where one side is only red and the other side is only blue. Same thing with the disk. Any line that you pick is going to incorrectly classify some of the examples. And then I guess the same thing with this third example as well. Any line that you pick is going to have on one side like some red and some blue. It's not going to be able to perfectly classify red, perfectly like separate red from blue. So I guess these limitations, so back in the 1960s or so, people realized, there was a book actually that described some of these limitations of single layer neural networks. And that actually had a massive impact on the field. So this was a book by Marvin Minsky and Seymour Papert from MIT. The specific thing that they, I guess, pointed out that you couldn't do with a single layer neural network is XOR. So that's the exclusive OR function. I guess I don't have it. Oh wait, no. The first example actually corresponds to XOR. So they basically realized that you couldn't do that. You couldn't implement an exclusive OR function with a single layer neural network. And then from that, they kind of convinced people to essentially stop working on neural nets for a while. So that was the first like winter of this kind of machine learning back in the late 1960s, I think early 1970s. All right, so I guess the answer to that, which I think even at the time like people realized, but somehow it didn't like permeate the field, is that you can move beyond single layer neural networks, and we'll describe how to do that in a bit. The other question I guess I haven't addressed yet is how do we actually choose like the weight term and the bias term. So I just described the computation that you do with a single layer neural network, but of course ultimately we want to learn what the weight vector and the bias term should be from labeled data. All right, so I guess I'll switch to describing that, unless there are any questions on this. Go ahead.
Does the temporal expansion methodology propagate to like n layer neural networks, or like
Yeah, so it doesn't directly. So yeah, the template matching is like specific to a single layer neural network. You can think of multi-layer neural networks, which yeah, I guess we'll describe in a bit more detail, as doing the template matching like over and over again in a kind of like abstract like space. Like you start off with the input, you do some template matching, and then that gives you some output, and then you do template matching of that, and so on. So you can think of it in that way, but yeah, at least just the kind of vanilla template matching interpretation that I gave is just for a single layer network. Yeah, other questions? Okay, let me switch to the board and then describe how we can go about doing the learning for the weights and bias.
How does that red and blue section example correspond to XR?
Yeah, let's see. So XR is so it's 1 if so it takes in like 2 Boolean like variables as input. So it's 1 if I guess if and only if, or let me write it like this: if x is 1 and y is 0, or y is 1 and x is 0, and it's, yeah, I guess it's 0 otherwise. So yeah, in the picture, yeah, so if you think of not Boolean variables, but like x and y are like positive and negative,
Okay.
like that's the correspondence.
That makes sense. Thank you.
Okay. Yeah, good question. All right, other questions? Okay. All right, so yeah, I guess let's think about how to learn W and B given data. And just to keep things concrete, let's think about this kind of pedestrian classification example. So we have some data set that we're given corresponding to images. So each image we're going to think of as a vector, and the superscript is going to index the different images in our data set. And then we have corresponding labels. So these are y1, y2, and up through y capital N. And these labels are just 0 or 1 for the sake of concreteness. So basically what we're going to do is try to find some W and B, some weight vector and some bias that will allow us to match the data that we're given as part of our data set. So this is called empirical risk minimization. Or ERM. Yeah, so basically find W and B such that the resulting function fits the data well. And yeah, I guess we'll be a little bit more precise about exactly what that means in a second. So we need to say what do we mean by fits the data well. So I'm going to pick a particular activation function. So we're going to choose sigma, which again is a mapping from a scalar to a scalar as this specific function. So it's going to return positive 1 if the input is positive, and it's going to return 0 if the input is less than or equal to 0. We can then define a loss function. So this is going to be a function that tells us how well any particular W and B does on any particular image and label. So the notation I'll use is little l, so that's going to be our loss function. It takes in 2 arguments. So one is the predicted, or you can think of this as the predicted label, and the actual label, yi. And this function outputs 0 if, actually let's give this a name, so this thing, we call it yi predicted. So if yi is equal to yi predicted, and 1 otherwise. Yeah, so basically this function is looking at the prediction given a particular W and B, comparing that with some true label, like whether there actually is a pedestrian or not. And then if the prediction matches reality, then we assign a loss of 0. If the prediction doesn't match, then we assign a loss of 1. So we can then sum over all the data in our data set, calculate the training loss. So we're going to call this capital L, which we can think of as a function of W and B. And I'm just going to define this to be the average. So n again is the number of images that we have in our data set. So it's the average loss on our training data set. I'm sorry, that should be. Should be an I here, so it's the ith image. Right, so we're looping over or summing over all the images in our data set. For a fixed W and B, if we think of this as the predicted label, like whether there's a pedestrian or not, we can compare that with the actual label. That gives us a loss that we average over the data set. Question?
Right, and then for the loss, you just like subtract the two and then like square it.
So here we're not using that version of the loss. I guess the loss function we're using is what I wrote over here. So we're just looking at whether the prediction, like the predicted label, which is like the output of the single layer neural network, matches the true label.
If you do subtractants, would it be a fraction?
Oh, I see. Yeah. So it would be equivalent. So in this case, since the activation like just gives you 0 or 1, yeah, you can also write. I guess we can write it like this. So yi minus like this thing squared. Yeah, it would be the exact same thing in this case. All right, other questions? Okay. All right, so what we're going to do then is find some so we can choose W and B, the weights and bias, to minimize our training loss, like to fit our data as well as we can, so to minimize this loss function. And all right, so I guess this is one specific choice. So we chose a particular activation, which is over there. We chose a particular loss function, and then we can try to minimize this training loss. The challenge with this, well, I guess there are a couple of challenges, but one challenge is that this is a hard optimization problem. And it's hard because things are kind of not smooth, right? So if you try to visualize this, of course, this is all in a high dimensional space, but if you think about, let's say, kind of W and B on the x-axis and the loss, the training loss on the y-axis, then it kind of looks like this. So it's like flat in some portions, and it's discontinuous. So if I change W and B a little bit, my prediction could go from being correct to not correct. Well, actually, sorry, I guess, yeah, this is fine. So like the prediction on one of the images could go from correct to not correct, and that can discontinuously change the loss question.
The training loss for is it one over factorial?
Oh no, sorry. This is just this is on the blackboard. I can't. Sorry about that. Yeah. It's just like things like paint or something on the blackboard. Yeah. So just the average, just the average across the different examples. All right. Other questions? Okay. All right. So how do we get around this challenge of non-smoothness? So we can try to smooth things out. So instead of choosing discontinuous functions for the activation and for the loss, we can choose something that's a bit more smooth. So one choice is what's known as the sigmoid activation. So in this case, we'll choose something that goes from 0 to 1. Asymptotically approaches 1. So as the input, so this is, let's say, the input z, and this is sigma of z. So as the input gets more and more negative, sigma outputs something that's closer and closer to 0. As the input gets more and more positive, sigma outputs something closer and closer to 1. And yeah, I guess the specific form of this is 1 over 1 plus e to the minus z. That gives you this kind of sigmoid curve. And yeah, I guess as we were saying before, you can kind of loosely interpret this as a confidence for whether or not the label is 1. So if the output sigma of W transpose X plus B is close to 1, you can kind of think of that as corresponding to higher confidence that the label is 1. If it's closer to 0, then you can think of that as higher confidence that the label is 0. But again, like I said, you have to be like really careful about interpreting those, like taking it too seriously. All right, so that's one option for the activation function. We can also choose a different form for the loss function. So one popular choice is called the binary cross entropy loss. So again, this loss takes two things as input, so the predicted label and the actual label, and it outputs a scalar. So here's the specific form. Yeah, I should have got a visualization of this, but if you plug in numbers, if you plot this as a function of the two arguments, what you'll see is that this assigns lower loss if the prediction is close to the actual. And higher loss if the prediction is far away from the actual label y. The good thing about this, I guess, as compared to the previous loss function we had chosen, is that this is continuous. So I can change the y predicted, like the predicted y, a little bit, and that's only going to change my loss by a little bit. And yeah, I guess the benefit of that so the benefit of using this specific activation, the sigmoid activation, in combination with the binary cross entropy loss, is that it smooths out the loss landscape. So instead of the loss kind of looking like that, it looks more like continuous. And yeah, I guess what this means is that we can use gradient descent or its variance to optimize the training loss. All right, so we'll I guess spend more time doing that in the next lecture. I'll describe the basics of gradient descent and some of the variants that are used in the next lecture. But I guess any questions on this? So yeah, I think yeah, we'll do two things in the next lecture. So one is talk about multi-layer networks. And then talk about optimization. Of the weights and biases. And the last thing we'll talk about is actually like super important, which has to do with generalization. So the scheme that I described so far, so we're choosing some weights and biases to minimize the training loss, like to fit our training data as well as possible. But of course, in practice, we don't really care about our training data, right? Like we already have our training data. Like if we're given some image, some input in the training data, we know what the label is. What we care about in practice is given some new input, like given some new image, figuring out whether there's a pedestrian or not, or what I guess object is represented in that image. So that's what I mean by generalization. So generalizing to new inputs, new images that were not given to you as part of your training data set. And yeah, I guess getting neural networks to generalize can be tricky. It seems like most of the time, or a lot of the time, they seem to have some pretty good generalization out of the box, but there's some like tricks to making that work out pretty well. Okay, any questions on that? All right, I think that's all the, I guess, technical material I had for today. I have one maybe quick poll that I wanted to take. So this year, because of the academic calendar, we basically have an extra lecture. So in previous iterations of the course, I used to do the midterm review in lecture, but yeah, because of the way things were structured, it was like not possible to do it this year. So we have basically an extra lecture. So I wanted to get a sense for, I guess, what would be most interesting for the class to discuss. So this will be not next week, but the week, yeah, I guess the week after that. So I have some possibilities, and maybe I can send out a poll later as well. But this is a quick informal poll here. So in the next, I guess, 2 or 3 lectures, we'll talk about multilayer networks and different architectures like convolutional neural networks for doing computer vision. So I guess one possibility which we didn't do in previous lectures is to talk about some reinforcement learning. So not just supervised learning problems, but yeah, getting like a robot to learn to do something via trial and error. So that would be one, I guess, possibility for what to talk about. The other possibility would be to talk about robotics and language. So specifically in the last, I guess, 5 years or so, there's been like a massive amount of progress on large language models. I mentioned this a bit 2 lectures ago. And yeah, people in robotics are trying to take advantage of this progress in language to do many different things. So I think that would be another possibility. I guess the third possibility would be to talk about some broader topics, let's say, in robotics and in machine learning more specifically. We'll do this a bit in the very last lecture. We'll talk about the impact that robotics might have on the economy, the intersection between robotics and the law, and kind of 1 or 2 other similar things. But I guess I was thinking, talking more about fairness, for example, and maybe a couple of other related topics could be another possibility. Yeah, what do people think? Maybe I can take a quick show of hands. So if you're If you want to think about, or if you want to spend time talking about who won, maybe raise your hand. Okay, quite a number of people. All right. Maybe the second one. Okay, all right. I guess I might have to count. Sorry, let's go back to the first one. I'll count quickly. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah, well, like 14 or so people. Okay. All right, the second one, robotics and language. Also about 14 or so. And then broader topics, it's going to be 14 again, right? 15? Okay. All right. I'll do okay. I guess I wanted to see those like a very strong opinion. Maybe I'll do I'll send out a poll so we can get more formal numbers. Are there other topics that people have like suggestions for that you'd really be interested in? Go ahead.
I don't know if it's applicable, but like some of the lower, like computer vision, like deep learning things.
Like transformers, for example, or?
Yeah, like the ones that are. I don't know if transformers are.
Yeah, that could be. Yeah. Okay, I guess that could be another possibility. All right. Yeah, other thoughts? Go ahead.
Like if we do the broader topics, learn about like surgical robotics or like more of the health with robotics would be cool.
Okay. All right. Good to know. Other thoughts? Good.
Maybe not just deep learning and its applications on vision, but also on control.
Yeah. Okay. Good. Yeah. So I guess that might. I was probably going to do that as part of the reinforcement learning, but yeah. Any other thoughts? Okay, sounds good. All right. Yeah, it should be fun. I'll see you next time.